Hello, everyone. Welcome to class 6 of the machine learning course. And before we begin, let me read you this ACM SIGGRAPH policy against harassment. This live stream is moderated by ACM SIGGRAPH. We ask that all comments stay respectful of others and respect ACM's policy against harassment. This means to exercise consideration and respect in your speech and actions. Refrain from demeaning, discriminatory, or harassing behavior in speech, and please be mindful of your fellow participants. All right, so let's get started. I am sharing my screen with you. This is class 6, and we have a lot to cover. And before we begin, let me welcome our guest, Ashish. Ashish is a senior research scientist in the Brain Group with Google AI. And he, just a couple of years ago, he came up with this transformer model, which has changed the field significantly. And we'll talk to him about it in a little bit more detail. So, Ashish, welcome to the class.
Hi, can you hear me well?
Yes, we can hear you and see you. That's awesome.
So just a second.
Sure.
Yep.
How are you doing?
Doing well. It's been an interesting year. I guess what it is now. What is it now? A year and a half, maybe? Yeah. It's yeah. So
No.
I'm lucky to continue to do research and yeah. So doing well, really well. Yeah.
Oh, that's awesome, and thank you for taking the time to be here with us for this class.
Thanks, Rajesh. Yeah.
And could you describe to our audience a little bit about yourself, like who you are, what the background you have, and how you got interested in machine learning?
Right. So yeah, I've been at Google Brain since 2016. Before that, I did my PhD, and I was also a scientist, a research scientist for 2 years at USC, the Information Sciences Institute, and in my PhD, my primary advisor was David Chang, and my co-advisor Leon Huang, and towards so it was a natural language processing with a focus on machine translation, but sort of towards the end of my PhD, I would say, like starting around late 2011 or 2012, I started getting intrigued by neural networks and deep learning, and our field at that time was beginning to see promise, but hadn't embraced it fully, or at least not as much as the field has embraced it now. And so yeah, I worked on like RBMs for figuring out like better feature representations for machine translation rules, neural network language models, feed-forward neural network language models inside machine translation systems, and then moving on to like sequence models.
Mm-hmm.
So that's kind of what movement sequence models for NLP tasks, like say super tagging and also neural networks for parsing. But then when I joined Brain in 2016, I sort of entertaining two options, either to continue working in sort of core NLP or sort of at Google, or to join the Brain Group. And I thought that Brain would be the place where I would be most excited to learn at the great set of colleagues. And so I joined Brain in 2016. That's pretty much, so PhD at USC, followed by sort of brief period as a scientist, and got excited at neural networks towards the latter part of my PhD, and then I joined Google Brain, which seemed like a pretty natural choice given what was happening in the field there.
No, that's a great career trajectory. And then could you describe a little bit of the history of models, like starting from RNN to gated units, to how you came up to with the transform?
So I guess the dominant model at the time for sequence modeling were these sort of LSTM based encoder decoders with attention, right? or like GRUs, basically the varieties that had explicit multiplicative interactions inside the models, like LSTMs and GRUs do. And they were dominant, and you know, a few of us as a teamwork, few of us thought that it would be a good idea. So the sequentiality of these models, the sequential computations of these models were limiting, and a few of us were thinking that, well, maybe we could do something like parallel decoding, and self-attention was a good candidate. And some of us worked on it, and that originally that path was the parallel decoding direction proved to be harder. And then we worked on sort of sequence-to-sequence models, more supervised sequence-to-sequence models for machine translation. And then other innovations like multi-head self-attention were added. And it's a process of, hey, let's try to let the sequentiality, or getting past the limit of sequentiality, which was inherent in these models, was sort of the initial goal for parallel decoding, but then it sort of evolved into sequence modeling. And then since then, yeah, it's been trying to sort of understand whether this primitive of self-attention, which had been around in the field, like they've been working from Google as well, and from other teams, like even I guess Montreal, Mila, yeah. And so since then, it's been about, you know, how universal is this primitive of self-attention, and then some of us have been pushing it in computer vision. So we had a paper in 2019, and since then, now it seems at least there seems to be a very positive trajectory for self-attention, even in computer vision. There's still some questions as to whether these models should be multi-scale, or whether they should embody locality like convolutions do for larger resolutions. So there's still some open questions, but it looks very promising at the moment, that something like a primitive like self-attention that has sort of parallelizability, also explicit multiplicative interactions, can serve well in multiple domains. Like multimodal models have also seen a very clear evolution with self-attention, and models like the transformer that use self-attention.
Right. No, I'm super excited to apply this to some of the vision issues that I'm working on. And then what is next for you? Like, if you can talk about your current research or future plans.
Right. So I'm excited about the application of self-attention to vision, and what would it give us? So in general, something like I get excited about emergent properties from our models. So things, you know, properties that we didn't exactly code for, but the model was general enough, and from the right loss in data, it manifests this property. So what would be an example of that? An example of that would be something like emergent segmentation or emergent detection. So if you have self-attention, the attention maps start mimicking objects, shapes, and boundaries, and learns to localize just through pre-training. And you can imagine with large amounts of image text data, if these phenomena appear in the model, you could do a lot of there could be a lot of powerful downstream applications like reasoning, because the model exactly knows where the objects are. So that's what excites me about this multimodal world. I think I'm also excited about the power of self-attention for generative models. It looks like it's a clear inductive bias. In fact, originally in vision, researchers much before us had applied similar primitives like self-attention, for example, non-local means. So its ability to model self-similarity could be quite powerful for modeling emergent phenomena like emergent segmentation or detection or generative models. So that's what excites me kind of the most these days. Yeah.
No, that's awesome. Looking forward to seeing more papers and good results from your research. Thanks. So just to wrap things up, do you have any advice to give to people entering the field, new students, people working on different kinds of problems? What should they focus on?
I don't think so. No, I don't really have advice. I could just share what I'm excited about, and as I did, it's no, I'm sure that somebody, people are as there are a bunch of, I guess good colleagues is a really awesome is a really is a superpower. We had great people working on the transformer, and work with fun colleagues, and it's not really clear whether there's some just I guess I could just share what I'm excited about and then share my enthusiasm for things, which is probably the best way I can infect people or give advice, but nothing really explicit. Yeah.
No, that's great advice. I think I've benefited greatly from collaborating with the like-minded people. One of the questions people have usually is when they're getting started, there are not enough resources because they look at billion parameters things being trained and they get discouraged a bit. But I'm sure there are ways to make progress without having to run very, very large models or spend like millions of dollars training.
That's an excellent question. Yeah, so an exciting thing about our field is that it's very active, and there's also a lot of opportunities to find like commonalities between different. For example, we're seeing a lot of ways of doing mixing spatially. There's been a flurry of papers with that are entertaining different approaches to do spatial mixing other than self-attention. So it's also interesting, and it's hard to sort of understand what primitives bestow or give what kinds of properties to models, and possibly leading to models that work better at all scales. So I guess one advantage about a lot of our one advantage about machine learning research is there's a wide expanse of very, very large models. We're knocking at the doors of extremely large scale. So sort of very performant models that possibly show a lot of promise at small scale could have immense impacts at large scale. So I think there's people should continue working on understanding what properties they want from their models, what properties data can give their models, and what general computational primitives or inductive biases allow these interesting emerging phenomena that you care about. Like, for example, I mentioned, for example, detection, or there's been a lot of great work on showing zero-shot behavior from models like GPT-3. So I think there's exciting problems at all scales of the problem, and of course, a new improved architecture will have tremendous impacts at scale. Yeah.
No, that's awesome. Thank you again for being with us and for your time. This has been a pleasure.
Thanks, Rajesh. Cheers.
Thank you. Bye. Thanks. All right, so that was Ashish, and again, thanks to him for being with us, taking time off his busy schedule. So what we'll do today is we'll do a quick recap of what we covered last time, and I'll go over some of the homework that I assigned last time. Hopefully you were able to play with the GAN and the CNN. We'll cover a bit of the variational autoencoder for generative models, and we'll complete our face detection that we started last time. And more likely we won't have time for covering the RNN and transformers, but we'll see if we can do that in the next class. So today's lecture, the slides are available in the Google Drive, and I uploaded a bunch of Python files in the Colab area. So make a copy of those in your own drive, and we'll access them and we'll use them today. So again, a lot of files, and let's just get started. So we talked about artistic style transfer with Leon, and this is from his paper. And what he described at that time was that he was using the gram metrics and in between layers of a CNN to extract basically style and content, separate them out, and then mix them in different ways. So alpha and beta here in this equation, they are the mixing constants, if you will. If you can mix the content and the style, and then into and come up with a third image, which has a mixture of both from two different images. So the actual algorithm, it takes a little bit while to run. So I uploaded a simpler model from Google TensorFlow samples, and you can play with that and try it out. It works pretty well for simple things. You can upload your own images and try things out. So I won't run this, but you can use that particular file to just play with it. It's really fun, and you can come up with some really bizarre things. And you can upload both a content image and a style image, and it'll mix them up. It's a nice thing to try out. So having said that, let's keep moving, and let's build a facial recognition system. So we said that many times we can use other models that have been pre-trained with the weights and everything set up. So then you don't have to retrain all of it. So you can either tap into one of the layers towards the end and add in some of your own data and train based on extra data, but it's not a whole lot of data. So the training is faster, and you already have this preset model, pre-computed weights that will help you kind of continue the training, and training happens really, really fast. And for that, you need to understand the model well. What kind of input would it take? A lot of the models will have their own little restrictions, like what sizes they will accept, what kinds of output they will provide. So when trying to use an off-the-shelf model with trained weights, you want to provide the data that it accepts in a way where it won't kind of fail on what you are trying to do. And also you want it to be general enough so that it's not so much dependent on the new data, or it won't change dramatically when you introduce partial new data. And best case, what you can do is that you choose a model that doesn't need any new data. It will still work with without extra training. So you can just use it like as a black box and just rely on the output of it. So we'll do that with the empty CNN that we talked about last time. It was the multitasking CNN that recognized faces in images. It didn't recognize them. It barely detects them. So it just says that here is a face. It doesn't know whose face it is because it's general enough. So it will work for all human faces. And we tried it on this Disney image with the characters from the films, animated films, and it was still able to recognize human-like faces, even though they are super stylized. So that's pretty good. So we can try it on our own images. So let's see what a facial recognition system might look like. So it would be a setup, something like this image that I'm showing, where you have a camera and somebody walks up to the camera and you look at their face from the camera, take an image, and you want to match this face with an existing database you might have of people who are authorized to enter an area or for whatever purpose. So essentially, you would need some kind of a ground truth to compare this new image. And this new image may have, that is taken from the camera, it may be slightly angled, it may have different lighting, and it may be few years old where the person has changed slightly. But overall, we want our facial recognition system to be robust enough to kind of not have to worry about all those changes in lighting or angles or age, and still be able to recognize that face. So putting this in a graphic form, when you're designing the system, you make these big boxes where you try to figure out what the components of this system might be. So again, there's no machine learning here. This is just you're trying to figure out what a system of facial recognition looks like. So you have an input image that you got from the camera or somehow, and you extract the face out of that image. So there may be multiple people standing in front of the camera. You want to extract the faces out of it. And you also have a database of known faces, where you will then compare this extracted face to all the known faces in the database. And then if there is a match, then you can say this person is authorized or not authorized if there is no match. So as you can already see, that we can start building up the software or the hardware needed to create this system. So first thing we'll do is the MTCNN part, which detects faces in images. So we covered this last time. So there's a paper for multitasking CNN that can do this detection for us. So we'll use that. So next part would be then creating this database of known faces. So we will take this database of known faces, and in a practical situation, this may be when an employee first registers through HR or other places. You can then capture their image and store it in the database. So to compare the images is a tedious task. You don't want to compare pixel by pixel because it doesn't give you much information because of the shading information change or age change or angle change. So the pixel by pixel comparison is not only going to be very slow, but it's also going to be probably wrong in many cases. So you want some other way of storing the known faces. So one way to store things like that is to encode them somehow. So encoding helps us with two things. First is that if the encoding is smaller than the original image, then the comparison time is less because you don't have to compare as many things. And secondly, if we can make our encoding invariant of the shading and invariant of the angle and invariant of the, then we can have so then our problem is to now figure out what could such encoding and a database of known faces might look like. So for that, we will use something FaceNet. So FaceNet is a model. It comes from a paper that I linked here. And what it does is, essentially, it has trained a lot of faces. There is a faces in the wild data set that has hundreds of thousands of faces. And this particular model encodes that in a as a 100 numbers, basically. So if you feed it a face, you will get out a set of 128 numbers. So you can think of it as a 128-dimensional encoding of the face, which uniquely identifies that particular face. And so that's how we worry about it. So in this particular case, we don't have to retrain this. Each face will be encoded in some unique enough 128 set of numbers. The way this loss works is it's called the triplet loss because there are three loss components here. So if there are two faces, say A and P, so that the A and P are close to each other, then you want them, the difference between them, to be as small as possible. But if you have two faces, A and N, which are very different from each other, then you want them to be as far as possible in this 128-dimensional vector. So by doing the negative, makes loss negative, and this is positive. And alpha is just a factor of how different you want the similar faces to be from the disparate faces. So again, think of them like a reverse magnet, where things are kind of similar to each other are closely clumped, and then things that are different from each other are as far as possible, but they are close to the things that are similar to that particular thing. So this clusters happen, and then the numbers then basically it's a vector of 128 numbers, and you can take a vector distance. So vector distance is just you take dot product with itself, and then you get a single number. So you can get a single number as a differential between two images, and the smaller that number is, the closer the images are, and vice versa. We'll try to use this model as well, and then build up our facial recognition system. So let's look at this file. So we'll install a package that we need. This is essentially how many of the packages store their models is in this H5 format. It's a compressed format for storing things, and it's a general enough format, but we can store the models in the weights. So the model itself is pretty small in compared to the number of weights in the weight files. The weight files are going to be huge, but the model itself should be pretty small. Then we load our TensorFlow and other related libraries. And just like last time, we're going to open up the empty CNN model. And next step, I'm going to use some trick here to mount the Google Drive directly into Colab. So if you use these couple of lines, it will mount the line on your Google Drive. You have to give permission to Google to make sure it can access the content of your drive. And what I have done is I have loaded the FaceNet model that is available as an H5 compressed file. And to be able to access that file, I'm going to give Google the permission to look at my drive. So once I do that, so let me mount this, and it's already mounted. I did that earlier in the day. And when it's not mounted, it will ask you for a password. Then you can give the password, and it will link your Google Drive here in this cloud machine that is already running. So let's look at, so if you click on this drive icon or the folder icon, you will see that it has mounted my entire Google Drive. There you go. So this is all of the Google Drive along with my drive. So you will mount your own drive, so you won't see my files. So if I go to this particular class, which is this folder, machine learning and neural networks. So then these are all the files that I've been uploading over the weeks. And this is where this model is stored. And by using this couple of lines, you're able to mount that. OK, so that's just a Google trick for working with the files directly from your drive. So mounted it, and just load the model. So now that it's already in the file system, it is going to be faster to load because you're not uploading it anywhere. It's already uploaded. So next thing we'll do is just what we did last time. We're going to load this file. So along with the model itself, I have also uploaded the images that a bunch of people sent me as examples that we'll use today. So these are the JPEG files, and I'm just going through creating a small dictionary here and going through the loop to just make sure that I upload or load all these files in this. Missing a comma here. So I got all these names and files. So basically a dictionary of file names and names that I assigned. So let's see what these images look like. Again, these are just faces of people, that's me and others. Okay, so it looks like a lot of people sent big files. And some of them are from last time. So okay, so we got some files that we're going to be using. So let's not worry about this whiten image yet. So let's do the first thing we can. We will encode each of these faces. So what we will do is for encoding the faces, the again, you have to worry about what this model accepts and what kind of things it will take. So you have to provide the data in that particular format. So this particular model takes 160 by 160 images. We'll resize our image to reflect that. And then because C works in a different way, we are going to encode them in so first thing we'll do is we'll face in the image using empty CNN, which we did last time. And then for each of the faces that was found, we are going to encode it. So, and to encode it, all we need to do is prediction on the FaceNet model, which will give you a 128 dimensional vector that you will save it out as the encoding. So that's all. So it's a loop that goes around each face, finds the face, and then encodes it using FaceNet. So finds it using empty CNN and encodes it using FaceNet. So there's a lot of stuff. So I'm going to take a very small break and see if you have any questions at this point. All right, any questions so far? Drink some water. Okay, so if you are following along, then let's continue. So now, when we give it a new face, what we are going to do is in that new image that you got out of the camera, you are going to find the faces. And for each of those faces, you are going to encode it. And then you are going to find the closest match to the stored faces. And that's it. This is basically software engineering, right? So you are going through a loop, encoding the new face, and then comparing it with the old face that you have stored. And if we can come up with some metric like how far this should be for between the existing face that you stored in the database and the new face, and if the distance is smaller than some number, then you can say that you have a successful recognition, and then we will draw something and put the name in there. And that's it. So so this whitening thing is kind of like normalization that the model requires. So you can do that. So think of it as normalizing an image, and that's all we're doing. Taking the mean and the standard deviation, and then subtracting the mean from the image pixels and dividing by the standard deviation. That gives you what is called in image processing a whitened image. Essentially, it's a normalization. So again, you have to know what the model expects, and good models will have all the details in their GitHub, what kind of things it expects and what to do and what not to do. Sometimes it can be bizarre because they will ask you for a BGR instead of RGB, or so if you have these small little differences, if you don't do them properly, then things don't come out right. So just be careful of when you do that. So all these things have. Now what we can do is encode all these faces. And then to test this, what I did was I put all the, so I have two images for each person. So the second image for each person, I put them in a grid like this. So they're all here. And this one came in at the last minute, so I just plopped it and took a screenshot. So now you have all these images essentially in a grid, in which I am trying to then predict if they match any of the original ones. So let's do that. Try to recognize this. All right, so let's see what it did. So looks like it recognized all of this. So if you are in the class and if you see yourself and you see that it succeeded or not. So it failed on 3 images. One was turned away, but then if you look at this original image for this person, the original images were in the beginning when we was this. But because it's turned like this, it probably failed for some reason. This person has closed their eyes and is making an expression, so that changed. This person, it failed because of the whole cosplay thing they're doing. And I was surprised by how good this came out, because this person submitted as their first image a front pose, but it was still able to recognize it even though it was in the side pose. So I think that's pretty good for this simple model we have used without training anything at all, and it's still working. So that's pretty cool. So go try it out with your own images and see. So there's some setup involved where you set up your Google Drive and upload the images so you can compare, but it's pretty cool. So with very little effort, we are able to do this, and then you can do this live. So I think if you can read a live camera image and then convert the video feed into a sequence of images, you can be doing a constant facial recognition system. You can hook it up to your Ring doorbell camera, get a small Raspberry Pi with camera, you can have a home monitoring system. If somebody known to you comes into your home, you can instantly recognize them. So it's pretty fast, runs pretty fast. It's just comparing 128 vector to each of the stored images. And as you can see, that if you have like hundreds of thousands of people, that comparison gets slower because that's how many times you have to compare the new face. But overall, it still works pretty well. It also doesn't take into account if you just hold up a picture against the camera, because it will still work. It's not like the iPhone. So what iPhone does is it matches not just the image, but takes a whole, basically a 3D scan of your head. So it knows that whether you are alive in a way where it only works if you are a real person and not just an image of a person that is trying to open up. So the systems can be more robust and get better. So there you go. Simple way to get going with a practical use of machine learning. So while we are talking about facial recognition, I also want to talk a little bit about bias. So when you see a database like that has empty CNN is trained on, it is getting the images from the internet usually. So then what happens is, if you look at who in the world uses the internet, it is mostly the richer countries, mostly North America, Europe, other parts of the world where it's easily accessible. So this whole 35% of the population who is not represented in that data set. And that can be a problem. So it introduces a bias in your data set, and by connection into your training and your prediction ability. So it would manifest itself in ways which are kind of not good for the society. So you don't want to have a data set that is biased. If you are going to make important decisions based on machine learning, things like if say this kind of system was deployed for arresting people, and if you have only trained on a certain kind of people who are likely to be arrested, then you have already biased your data. So there's a lot of things like that can creep in to the machine learning system. Sometimes the research is okay to do on these kinds of models because you're purely focusing on research, but when you deploy it in practice, then it can be a problem. But a lot of time from research to deployment, people miss out on, they don't retrain, they don't get extra data. So you want to be careful. Every time you have data that you are trying to make some decisions with, think about and ask these questions, like, is this data biased or unbiased? How can I help it make it unbiased? And how can I train things so that decisions that I make are affecting society in a way that is positive or at least not negative? So that's all I'm going to say about that. But I think it's something important to keep in mind with any kind of vision-based system. All right. Any questions so far? So next thing we're going to do, I'm going to cover a little bit of variational autoencoders because it's an important model, and it gives rise to some of the math behind things. I've been talking about distributions and how to sample them, because that's what most of the time we are doing in machine learning anyway. So just to reiterate that aspect, and then to get it in your mind to think of things in terms of distributions and so when you look back at the autoencoder, so what we did was we had a network where we fed in data, and then we compressed the network down to some bottleneck layer in a latent space that was smaller, and then we tried to expand it back. We had some loss, but you were able to recreate the input pretty accurately based on how many things you had in the bottleneck layer or the encoded data space. So what we can then think of as a thought experiment, let's see, we have trained this thing, and on the handwritten digits, the MNIST data, and then we take it and break it apart right here in the middle, where these two encoded nodes, they are repeated, but then just the network is entirely broken and right in the center. So you get some numbers, say X and Y, out of this for two nodes. And if you feed those X and Y, you're going to get the 4, right? So now you can think like, oh, I can be clever. And what if I just make a small change to X and a small change to Y, small deltas, and I can get a variation of the 4. So that could be something you could try. And what will be the output for this kind of thing, where you have just a small delta, and because you think that X and Y regenerated 4, then some small delta might generate something similar to 4. In practice, that doesn't happen because the spaces for the input distribution and the one you have in the bottleneck layer, they are different. So when you sample from one, you don't get a sample from the other. So what you want is try to get in your encoding a distribution that is very similar to the distribution that is coming in from your data. So your 4s are kind of distributed in some way where all these 4s would be close to each other in that distribution. But when you come to your latent space, there's a different space. So delta might push you out somewhere else that is not a 4 at all, even if it is a small delta. So if you were to treat your bottleneck layer itself as a mean and variation of a distribution, and then we can try to see if we can minimize that loss as a distribution loss. And we can then come up with new mu and sigma that is as close to the distribution of the input data. So what would then happen is you would get, instead of treating them as some X and Y, you get the mean and the variance of a distribution. And when you train all of this, you would essentially get back a distribution that is similar to the input distribution. So there is some gnarly math involved here, which is when you want to create a loss function that is the difference of two distribution, you have to figure out what it means for two distribution to be close to each other. There is a KL divergence loss or KL divergence theorem that kind of tells you how to compare the two distributions, and the math is a little bit we're not going to cover that, but just keep in mind that there are ways to compare distributions and how far they are apart from each other. So now that you have this mu and the sigma, and after you train it and then break it up, now you can do deltas, and you can take this because we know how to sample a Gaussian distribution. Remember in the second class or the first class when we did the least squares, we knew how to sample that Gaussian distribution is a bell curve essentially, and you can easily sample from that. At that time, you would get back things that are similar to 4, and you can start varying this as much as you want, and then you'll get things that are far from 4. So next thing you can do then is train the 5s and train the 6, and all this, you'll get different mu's and sigmas for each of the letters. And then you can start getting creative where you can mix and match different distributions and interpolate with them, because they're all approximations to a Gaussian distribution. You can do a weighted average of multiple distributions. So think of it as a clustered thing like that, where these ones are that are in this yellowish color, they are a distribution. The 6s are a distribution. 0s are a distribution. So you will get a mu and a sigma for each of those, and then you can start interpolating between the two. So then you can have a generative model which is going smoothly from the 6 to the 9s. So you'll see these examples in a lot of things people put out, like a celebrity transition or some kind of a morphing that happens from people with glasses to people with no glasses, or a blonde hair to a redhead. So all those things are done using this kind of interpolation scheme of different distributions. It's pretty cool, and it looks really nice. So take another small break, and let's see if you have any questions. And okay, so all people be crazy. How would you ensure the data is not biased? So you want to think of again in terms of distribution. So you want to cover as much of the distribution. So if you say this data is of humans, then that's a pretty big distribution. And you want to see, am I covering all human beings? Am I covering a good sample of the human beings on Earth? What kinds of data are not being represented in my data set? So if you only look at the internet to collect data, or if you only look at celebrities to collect the data, because those are the images readily available, right? So then you can say, like, okay, I don't have images of people from Africa. There are not enough of them, or from India. What am I going to do? So are you going to then, because that's expensive then, to collect real data that is not readily available, you are going to have to send people to take pictures and collect their pictures and images, or run a survey of some kind. So you want to fill out your distribution as much as possible. So as you are learning to do things, it is okay to try out data that is already there. So even in this MNIST data that we have, right, it is somebody's handwriting. Does it cover everybody's handwriting? Probably not. It covers a few people, maybe, or maybe it's just the same person who, like, I don't know how exactly this data came about, but most likely it is not covering everybody's handwriting. So you want to ask these kinds of questions, like, is my data filling out the distribution that I'm going after? So if not, then you want to specify in your solution that this data was gathered from the internet. It only contains celebrities. So what it is outputting only applies to that particular kind of distribution that I have. So you don't want to generalize your answer to every human being based on just the celebrity database. All right, that was a long answer to a short question, but good question. All right, so let's switch gears and then think about what. Well, this is something I wanted to show you. It's projector.tensorflow.org. It has some visualizations of different kinds of data that I've been showing, and it lets you try out. Like you can get the MNIST data. So it's kind of nice, actually. It lets you visualize interactively the distributions, and it does something called principal component analysis to figure out the different axes or the latent spaces that your data might reside in. And the idea is to basically cluster them in a way so that your latent space shows things that are close to each other. So PCA does one version of it, and then there is something called the TSNE algorithm, which does a better job of clustering things that are alike together. So as you see, as time passes by, it is going to start clustering things that are alike together. Anyway, it's a pretty cool tool. Play with it, see what you think. So as I said, like each of these is now a distribution of some kind. And when we use a variational autoencoder, they are Gaussian distributions that we have kind of found that are closest to our distribution. And then from there, you can start interpolating. This was a 4, this was a 5. And then if you just vary this sample, that particular distribution, you'll get some kind of a 4 in between. But if you mix and match the red and the green distributions, you get a smooth transition between the two. So what you do is you find the center, which is the mean, and then do an interpolation between the two distributions. All right, so switch gears. So we've been covering neural networks so far, which take in data, don't remember the previous data at all, and just rely thinking of each data point is independent, and all our decisions are based on a time step that goes on. So recurrent neural network are kinds of neural network that basically contain references to previous data points. So that allows it to kind of provide answers in context. So if you have a sentence, for example, I went to the beach, then it will know that the went and to, they go together. So it has some sense of time step, or it has some sense of connectedness to the input that that happens over time. So this is very useful for things like text translation. So if you have any kind of translation that you see, either through Siri or Google Translate, they all follow some kind of a network that has this mechanism in it, that is basically providing for context during translation. And it works pretty well. And there have been a lot of advances in this area, because this natural language processing is a big step towards getting this generalized translation scheme. So you can do this for languages or for music, any kind of data that is temporal in nature, which is basically means time dependent. it's a little bit complicated to set up, but there are things in TensorFlow that help you set up. So RNNs were like, they work pretty well, but then they take a lot of processing and time. Because you need to maintain the context. The longer context you need to maintain, the more data needs to run together, so they are slow. And so there's also, because you're holding all these weights for a longer period of time, and they change over time, there are problems with, we mentioned before, things like exploding gradients and vanishing gradients. So they're both an issue. In the exploding gradient case, the gradient over time becomes so large that it becomes like a huge number, and it unduly starts affecting your output. And the opposite case, where the gradient becomes very small and almost zero and stops updating altogether. So there are both these issues happen with RNN. So there are mechanisms to kind of make these faster, make these better, have better context, and one of them is called GRU, which is an RNN with a memory state. So again, mathematical operations essentially inside that kind of once in a while will keep the things that you need for an extra bit of time, and so you'll get more context. So again, don't worry about all the math involved here, but the purpose of it is to kind of just hold things in memory for just a little bit longer. And what we talked about with Ashish today was the transformer or tension, which is a big step forward because it lets you process things in parallel and makes things much, much faster. So they are the kind of new word on processing any kind of attention-based mechanism or any kind of temporal connection between inputs. So that's what has essentially taken over the field now, is the transformer. So we'll cover that maybe next time. Structurally, they should be similar, except they work in parallel. And the results have been astonishing, actually, pretty good. So let's try this. Let's try this for text generation. So what we can try to do is we can input some letters and try to see what the next character would be. So the way you set these things up is you pick a sequence length that you want to try it out, and then you divide all your text into these sequences. And then you train on your sequence plus one more of you can choose words or letters or sentences. So you train the current sequence and the next sequence, and so that's your pair. So you keep training in these pairs so that you have this connectedness where you say, I'm saying this input machine without the E, and then you can expect the next set of output to be the rest of it, so which is this. So in this case, our sequence is characters, and then +1 is the +1 character. So the next output would be this plus the next character. So that's how these things are set up, and do exactly that. So what we'll do is we'll try to teach machines to speak like Shakespeare or write like. So go over this again, loading packages that we need. So what I did was I uploaded basically an entire act from Hamlet, all of it right here. So that way we don't have to upload any data. So then we do some text processing. So remember, all machine learning works on numbers. So we'll have to convert things into numbers. So before we do that, first we find out the vocabulary. So we'll go letter by letter because that's faster to train. If you go word by word, you have a very large vocabulary because there are more words than characters. There are 26 characters in the English language, but words could be like 100,000, right? So you want to have a small vocabulary to be able to train faster. So we will train it letter by letter. So once you just some string processing, we'll try to find out what our vocabulary is. So it found out from this text these are the things that are in there. So actually, it's not just 26, but it's 26 uppercase, 26 lowercase, and some punctuation marks and other things. So there are 62 items in our vocabulary. So next, what we'll do is, because we need to convert everything to numbers, we will enumerate that, and then we just convert it to numbers. So essentially, we've assigned to each of the items in our vocabulary a number. So we can then map it back when we need to, when we on the other side of training. So let's see, the first line itself is being mapped to these numbers. So the neural network will see just these numbers, and it doesn't understand words. So we convert this to numbers and send it back. So for the prediction, then we will set it up, as I said earlier, as a small sequence, and then start training it. And I'm just going to batch some data, just look at the data. And again, mostly just data processing here. There's no training or anything we're doing. So ultimately, we're just prepping it so that when we get the output, we are going to convert it back to the letters that we had, and we're going to set up pairs of the ground truth. So if the input is S, we are expecting the next one to be C because of this scene. So we're setting up these pairs of what to expect as the ground truth so if your input is E, the next one you would expect is N, and so on. So let's train this. Set up buffer size. And this is our RNN. So essentially, you're embedding this in a higher dimension, and then this is the gated recurrent unit that we are setting up. And we will, at the output, you would have basically a 62 node layer, and each of those would give us the probability. So we'll pick the one with the highest probability as the next character. So at any time you get an output, you have 62 possible choices, and they'll all get probability because we use a loss that is similar to the loss we use for classification. And then we build the model, and then we take some sample, run it. Again, imagine the number of parameters is huge, so it will work. So we're using this categorical thing again so that we can get the probabilities. And we're just sampling it. So if we run it without training, it is outputting some gibberish, which is good. Which is exactly what you would expect because it's not trained at all. So now we are going to train it with the categorical cross entropy, which means it will give us the logs, and then we would convert those to probabilities and choose the one with the highest probability. Combine the thing, and then we'll keep a checkpoint so that we know how things are going. And then let's run this. So this takes a while to run, 18 seconds per epoch. So I will let it run. So now, like initially, we saw that it was all random. So we give it a little bit of a starting thing, and you can see that it is trying to now understand words at least, and it has some form of English sentence-like structure. So it is learning and being better, although it's still gibberish. So if you train it for a little bit longer, you will see that it will start outputting strings that are similar or in nature to the Hamlet, but at least it's now getting the structure right. It knows that it has to do these speaker uppercase things from time to time, and all these are like word-like things with some punctuation. So it's just understanding some of the ways to generate it, and over time it will start generating fully. So we're over time, so let's stop here. Again, play with this. You can take this thing and put in any other text you want. Make sure you separate it with new lines here like this. You can even enter text in another language. You can take the UTF character set from a different script altogether for Devanagari, for Hindi, or put in Spanish. It will still work because we can put everything to numbers. It doesn't care about what the language is. So try it out with different languages, different text, and see how it goes, and train for a longer time, and you will start seeing it do better. All right, so let me go back to the thing and see how things are going. Any other question? If the system is being trained using artificial images, not from nature, but visually, would it be difficult to discern by the human eye? Such data will be viable substitute for the... Yes, so I think a lot of times we are doing that now in the industry. You can create simulations that are indistinguishable from real images, especially with the ray tracing. A lot of the times you're not able to get the data that you need. So for example, like say if Tesla or Google were to training to do this self-driving, you can drive around the world and try to find the distribution of all possible roads and conditions, but that's like expensive and not plausible. So what you can do instead is recreate these environments in a three-dimensional, like a game-like engine, where it is realistic enough. So then you can fill out those distributions, things that you can never go to get actual data, but you can now generate. Not only that, but you can generate these things in parallel. You can have these multiple environments created. Same thing with robotic. If you can do a physical simulation, you don't need to build actual robots to get the data. You can get a very good data from simulated robots. So yeah, no, that's a big field itself, like getting simulation to generate data for you for your training. Very good question. All right, let's end here. And next time we will cover reinforcement learning. And Dr. Andrew Klasner, he will be presenting the class almost in the entirety. He's an expert in the area, also knows about rendering. So it will be an honor to have him come and join us the next time. So I'll see you then. Any questions, send them to my Twitter account or connect with me on LinkedIn. Bye, everyone.
At SIGGRAPH 2020, more than 10,000 individuals from 95 countries gathered virtually to experience over 350 hours of content presented by more than 1,600 contributors. What resulted was pure SIGGRAPH. Robotic advances use subtractive fabrication techniques to carve foam and similar materials like an artist. Modeling and predictive computation creates a more robust and accurate time-stepping of nonlinear elastodynamics. New investigation into damage simulation could change the landscape of video and game effects, as well as surgical training. Novel healthcare technologies point toward new ways to transform and enhance lives. Research will help users to create reprogrammable multicolor textures made from a single material. AI-driven technology pushes the capabilities of crowd simulation. Award-winning animation showcases the latest in computer graphics. Real-time and gaming technology advancements transform interactive storytelling techniques and explore new applications of the technology. Evocative digital artwork uses machine learning to create visceral experiences. Now is the time to share your research, your innovations, and your creative inspiration. SIGGRAPH is your community, and we hope you'll share your work with SIGGRAPH 2021.